Hello everyone, I hope you're all safe and sound. Welcome to the ninth lecture on analog and digital electronic circuits, in which we will study multi-stage amplifiers. So after introducing multi-stage amplifiers, we will study their maximum symmetric swing, and I will illustrate the concept with an example of a three-stage amplifier. Then we will study different multi-stage amplifier configurations, namely the capacitive coupled multi-stage configuration and the direct coupled multi-stage configuration. And we will analyze these two configurations for the DC currents and voltages and small signal parameters. So the motivation behind the use of multi-stage amplifiers is the fact that often single-stage amplifiers, they do not meet all the design requirements of input impedance, voltage gain, current gain, and output impedance simultaneously. So if we talk about common emitter amplifier, then it has moderately large input impedance, good voltage gain, good current gain, but moderately large output impedance as well. Similarly, for the common base amplifier, the input impedance is very small and output impedance is moderately large, both of which are undesirable attributes. Whereas for the common collector amplifier, although we have moderately large input impedance, but it does not have any voltage gain. Voltage gain is almost unity. So we can see that single stage amplifier configurations, they do not meet the design requirements of all of the small signal parameters collectively and simultaneously. So instead, what we do is we connect different single stage amplifier configurations in a cascade structure and obtain a multi-stage amplifier as shown here in this diagram. So the individual stages, they are designed to serve specific purposes. For example, this first stage, which is also called the input stage, this stage is designed to offer large input resistance. So typically multi-stage amplifiers use what is called as a differential pair as the first stage of the multi-stage amplifier. So unfortunately, we won't study differential pair in this course. But in addition to providing large input resistance, differential pair also provides immunity to noise. That is, it nullifies the effects of noise at the input of the amplifier. The middle stages, they are typically designed for the voltage gain. And this final stage, which is also called the output stage, it is typically designed to have large current gain or large power gain. So each of these stages, like I said, is designed to serve a typical to serve a specific purpose. And by cascading these different single-stage amplifiers, we obtain a multi-stage amplifier, which then satisfies all the requirements on the input impedance, voltage gain, current gain, and output impedance simultaneously. So as before, I represent the small source signal to be amplified by Vsig. Rsig models the internal resistance of Vsig, and Ri1 is the input resistance of the first stage, which is also the input resistance of the multi-stage amplifier. R01 is the output resistance of the first stage. Ri2 is the input resistance of the second stage. R02 is the output resistance of the second stage, and so on and so forth. So Rin is the input resistance of the nth stage, and R0n is the output resistance of the nth stage, which is also the output resistance of the overall multi-stage amplifier. RL is the load resistance, and VL is the voltage across the load resistance. So the overall voltage gain of the multi-stage amplifier, which is given by the ratio of VL to Vsig. VL is the AC component of the load voltage. Vsig is the source signal. It's given by this expression. It is expressed as in terms of the product of the voltage gains of the individual stages. So AV1 is the voltage gain of the first stage, AV2 is the voltage gain of the second stage, and so on. So Vsig, a fraction of which appears as the input of the first stage, that input is amplified by the gain of the first stage, and it becomes the input of the second stage, which is then amplified by the gain of the second stage, which then becomes the input of the third stage, and so on, until we get the input here at the voltage here at the input of the nth stage, which is then multiplied by the gain of the nth stage, uh, and then we get the output across the load. So this output in terms of this V sig is given by the product of the gains of the individual amplifier stages. Also, this factor here, this ratio, it takes into account the effect of loading on the input side. So, like I said, a fraction of V sig appears as Vi here. The other fraction is lost across R sig. So, Vi is Ri1 over Ri1 plus R sig times V sig. So, we take V sig to the other side, and this is the factor we are left with. So, this takes into account the effect of loading on the input side. And the gain of the individual stage, so the gain of the jth individual stage represented by AV, comma J, is given by this expression. For J between 1 and n minus 1. And for J is equal to n, that is for the nth stage, the gain is given by a similar expression. So AV naught J is the open circuit voltage gain of the jth stage, and AV naught n is the open circuit voltage gain of the nth stage. So please keep this in mind that these expressions, they are valid only for the case of unilateral amplifiers. So if the single stage amplifiers are considered unilateral, they can be replaced with this two-port unilateral model for the voltage amplifier, where this is the two-port unilateral model for the voltage amplifier in the jth stage. So Vij is the input voltage of the jth stage, Rij is the input resistance of the jth stage, R naught J is the output resistance of the jth stage, and Rij plus 1 is actually the input resistance of the following stage, of the J plus first stage, but that stage since that stage acts as the load, so the input of the second stage acts as the load to the first stage. Similarly, the input of the third stage acts as the load to the second stage. So the input resistance of the J plus first stage acts as the load resistor to the jth stage. So Rij plus 1 is connected as the load resistor to the jth stage. V naught J, which is the input voltage of the J plus first stage, is the output voltage of the jth stage. So this is the unilateral model for the voltage amplifier in the jth stage, and by applying the voltage division rule on the output loop, we can see that V naught J is equal to this voltage times Rij plus 1 over Rij plus 1 plus R naught J. So we get this factor here, and then this factor times this voltage is equal to V naught J, and then when we divide we divide V naught J with Vij, and we'll be left with A V naught J. So V naught J over Vij is the gain A Vj, and hence it is given by this expression. I have written the gain for the nth stage separately because for the nth stage, the load is the load resistor now. There is no stage connected at the output of the nth stage. It is just the load resistor. So this load to the nth stage is actually RL. So it's actually the same expression. The only difference is that I have replaced the load resistor with load with RL for the nth stage. But please keep this in mind that these are valid only for the unilateral model of the amplifier. And here I've represented the open circuit voltage gain as VOCJ. So if I remove the J plus first stage, this output of the jth stage will be open circuited. I denote that output voltage as VOCJ, and VOCJ divided by Vij is then the open circuit voltage gain. So you can see that if I remove this resistor, then VOCJ is actually equal to this voltage. So dividing by Vij, we get VOCJ over Vij as AV naught J. So this is the open circuit voltage gain of the jth stage, and similarly, this is the open circuit voltage gain of the nth stage. So it should be VOCN, which is the open circuit output voltage of the nth stage, divided by Vn. So this should be N. Please make this correction. AV naught n should be VOCN divided by VIN, the input to the nth stage. It should be VIN and not VIN minus 1. So what if the amplifier is not unilateral? Because if you remember, when we analyzed common emitters, common base, and common collector amplifiers, all of those amplifiers, uh, if we consider small r naught, well, common collector amplifier is not unilateral anyways, but common emitter and common base amplifiers, if we consider small r naught, then they are not unilateral. Uh, so what if these single stage amplifiers are not unilateral? Then we'll have to find the voltage gain just the way we did for the common emitter and common base amplifier. Uh, Replace these individual stages with their AC equivalent circuits, and assuming the input resistance of the following stage as the load resistance of the stage under consideration, you just derive the ratio of the load voltage to the input voltage of the of the stage under consideration. So the load voltage is actually the input voltage of the following stage, and you take the ratio of the load voltage with the input voltage of the stage under consideration, and you will find the voltage gain, which will be different from this expression, because this is the expression only for the valid for only for the uh, unilateral amplifier. Please also note that for the common emitter and common base amplifiers, when we derive exact results, then after deriving the exact results, I made some assumptions which simplified the exact results. So all of those assumptions were about small r naught. So basically, I ignored small r naught when I made those assumptions, because I assumed that small r naught was much greater than the other resistances in the network and their combinations in the circuit. So this is equivalent to ignoring small r naught. So when I ignored small r naught, I obtained approximate expressions for the small signal parameters of the common emitter and common base amplifier. So ignoring small r naught makes the common emitter and common base amplifier unilateral. Approximately, if you ignore R naught, then you can treat the common emitter and common base amplifiers as unilateral amplifiers. So the approximate results that you obtained by ignoring small R naught, they are the small signal quantities for the unilateral amplifier then. So if you go back to lecture 6 and lecture 7, where we discussed common emitter and common base amplifiers, and look at the expression, the approximate expression for the loaded voltage gain, AVJ, excluding the factor of loading on the input side, because we have already taken this factor here into account. So in those approximate expressions we derived for common emitter and common base amplifier for the loaded voltage gain, if you ignore the expression for the loading on the input side, then the remaining approximate expression is actually exactly equal to this thing. So you can write that remaining expression in terms of the open circuit voltage gain in this form exactly. So those approximate results for the loaded voltage gain, they actually follow this form, which is indicative of the fact that ignoring small r naught renders the common emitter and common base amplifier as unilateral amplifiers. So we can find the maximum symmetric swing of a multi-stage amplifier in terms of the maximum symmetric swing of the individual stages. So we've already found the maximum symmetric swing of the individual stages, because these individual stages, they're either common emitter, common base, or common collector amplifiers, and we have already found the maximum symmetric swing of these three configurations. So using the maximum symmetric swing of the individual stages, we define the maximum symmetric swing of the multi-stage amplifier like this. So it is the minimum of these terms here. So what are these terms? So the first term is maximum symmetric swing of the nth stage. The second term is the maximum symmetric swing of the n minus first stage times the gain of the nth stage. So what we're doing here is that we find the maximum symmetric swing at the output of the nth stage, and then we find the maximum symmetric swing at the output of the second last stage. Since that output is multiplied by the gain of the nth stage, so we multiply the swing of the second last stage by the gain of the nth stage, and we get the contribution of the swing from the second last stage at the final output. So we obtain at the final output, we compute at the final output the maximum symmetric swing because of the output stage. We compute the maximum symmetric swing of the second last stage and multiply it with the gain of the final stage. And this factor here, this quantity represents the contribution of the second last stage to the maximum symmetric swing at the final output. Similarly, we find the maximum symmetric swing of the n minus second stage, and since that swing is multiplied by the voltage gain of the n minus first stage and nth stage, we multiply that swing with the gain of those stages, and this quantity is the maximum symmetric swing at the final output due to the n minus second stage. And we do that for all the stages. So all the way down to the first stage. So we find the maximum symmetric swing of the first stage, and then we multiply it by the voltage gains of the following stages to obtain the maximum symmetric swing at the final output due to the first stage. And then we define the minimum of these quantities as the maximum symmetric swing of the multi-stage amplifier. So whereas before AVJ is the voltage gain of the jth stage. So this just states what I explained, that the maximum symmetric swing of a jth amplifier stage is multiplied by the voltage gains of all the stages ahead of it to compute its maximum symmetric swing at the final output. So minimum of the maximum symmetric swing computed for all the stages in this manner at the final output gives us the maximum symmetric swing of the multi-stage amplifier. So I would like to illustrate these concepts through an example of a three-stage amplifier, which is excited with the source signal and is also connected to the load. So I assume that the gain of the first, second, and third stage, these voltage gains are 2, 10, and 0.9 units respectively. I also assume that R sig, as well as the output resistance of the third stage, they are 0. In other words, I am ignoring the effect of loading on the input and output side of the multi-stage amplifier. I assume that the maximum symmetric swing for the first stage is 1 volt peak to peak. For the second stage, it is 8 volts peak to peak, and for the third stage, it is 10 volts peak to peak. So given this information, I can find the maximum symmetric swing of the overall multi-stage amplifier by computing the different terms in this definition, these different quantities. So maximum symmetric swing of the third stage, which is the first quantity to be computed, is already known. So it is 10 volts peak to peak. Maximum symmetric swing of the second stage times the gain of the third stage is 8 times 0.9. So this is the second quantity. And then the maximum symmetric swing of the first stage, which is 1 volt peak to peak, times the gain of the second stage, which is 10 units, times the gain of the third stage, which is 0.9 units. This gives me the third quantity. So I have 10, 7.2, and 9 volts peak to peak, and the minimum of these three is 7.2 volts peak to peak. So the maximum symmetric swing of the overall amplifier, multi-stage amplifier, is 7.2 volts peak to peak. So in this diagrams, I analyze the voltage at the output of the stage 1, stage 2, and stage 3, which is given by black, green, and magenta curves, by varying the peak value of the signal, small source signal. So I excite this multi-stage amplifier with a sine wave of 1 kilohertz, So V sig is a sinusoidal signal of 1 kilohertz, and then uh, uh, I apply a peak. I set the peak value of the source signal to zero point 0.1 volts to obtain these voltages. So all is well in this figure. Voltage at the output of the first stage as well as the second and third stages, they are sine wave. But as soon as I increase the voltage, the peak value of the input voltage to 0.201, uh, the the output voltage at the voltage at the at the output of stage one is still a sine wave, but this green curve, which is the voltage at the output of stage two, I hope you can see that it is slightly clipped off at the top, and hence the voltage at the output of stage three, which is given by magenta curve, is also clipped off. Because once the voltage at the output of any intermediate stage it gets clipped off, then the final output will be clipped off. Because, for example, in this case, if the voltage here at the output of the second stage is clipped off, then this clipped off waveform is just scaled by the gain of the third stage, and we'll get the scaled clipped off version at the output as well. It won't change its shape back into the sine wave. It will just scale the voltage at the output of the stage 2. And since it is already clipped off, the output here will be clipped off. So the important point to note here is that if the voltage at the output of any intermediate stage gets clipped off, then the final output will be clipped off. And this is what we observe here. So this green waveform is slightly clipped off right at the top, which results in clipped off voltage at the output of stage 3 as well. So I hope you can observe this slight clipping at the very top of the peak. And when I increase the input peak voltage to 0.25 volts, then you can clearly see that the voltage at the output of stage 1 is still a sine wave, but the other two voltages, they are chopped off at the peak. So why at this value of the peak of the input voltage do we start to see this clipping off effect? So if we analyze this circuit, then the output swing here at the output of stage 1 is 1 volt peak to peak. So dividing this with the gain of the first stage, which is 2 units, I get at the input of the first stage 0.5 volts peak to peak. So as soon as the input here, the voltage at the input of the stage 1, it exceeds 0.5 volts peak to peak, output will exceed 1 volt peak to peak, and since the maximum swing allowed here is 1 volt peak to peak, so the output will be clipped off at this node. And since the voltage at the output of stage 1 is clipped off, voltage at the output of stage 2 and stage 3, they will also be clipped off. Similarly, if we analyze the swing here at the output of the stage 2, then the maximum allowed swing is 8 volts peak to peak here. Dividing it with the gain of the second stage, which is 10 units, I get 0.8 volts peak to peak here. And dividing by the gain of the first stage, which is 2 units, I get 0.4 volts peak to peak here. So when the voltage here is 0.4 volts peak to peak, the voltage here is 0.8 volts peak to peak, still within the maximum allowed swing, and the voltage here becomes 8 volts peak to peak, which is the maximum allowed swing. So as soon as the voltage at the input of the first stage increases beyond 0.4 volts peak to peak, the output here, the voltage at the output of second stage will be clipped off at 8 volts peak to peak, because it cannot go beyond 8 volts peak to peak. And hence, since this voltage is clipped off, the voltage at the output of the third stage will be clipped off. In a similar fashion, for the maximum swing here, which is 10 volts peak to peak at the output of the third stage, if I divide this swing with the gains of the third, second, and first stage, then this 10 volts peak to peak swing gives us the input of the third stage as, so 10 divided by 0.9 is 11.11 volts. So we get 11.11 volts, and then divided by 10, we get the input voltage here as 1.11 volts. And then divided by 2, we get the input voltage here as 0.55 volts peak to peak. So as soon as the voltage here increases 0.55 volts peak to peak, this output tries to go beyond 10 volts peak to peak, which is not possible. So it will be clipped. The final output will be clipped. But please note that the final output will be clipped before it reaches 10 volts peak to peak, because this when I apply 0.5 volts peak to peak here, then the output here, which is the gain of the first stage is 2 units. So multiplying 0.5 volts peak to peak with 2 units, I get the output 1.11 volts peak to peak. But this node cannot swing beyond 1 volts peak to peak. So the voltage here will already be clipped, which will produce clip voltage here and clip voltage here. So the important point to note, like I said, is that, like I said before, is that if the voltage at the output of any intermediate stage gets clipped off, the final output voltage will be clipped off. So we have found 3 peak-to-peak values corresponding to the maximum symmetric swing constraint of the first stage, second stage, and third stage. And the minimum of, so the 3 peak-to-peak values were 0.5, 0.4, and 0.55 volts peak-to-peak. So the minimum of these three is 0.4 volts peak-to-peak. So when I apply 0.4 volts peak-to-peak here, I get 0.8 volts peak-to-peak here, and I get 8 volts peak-to-peak here, and multiplied by 0.9, I get 7.2 volts peak-to-peak here. So as soon as the voltage at the input increases 0.4 volts peak-to-peak, we will observe clipping at this node, which will produce clipped output at this node. That is why the swing is 7.2 volts peak-to-peak. This 7.2 volts peak-to-peak at the output corresponds to 0.4 volts peak-to-peak at the input. So 0.4 volts peak-to-peak means 0.2 volts peak. So 0.2 volts, if I apply 0.2 volts peak, I'll get sine wave at the three outputs. But as soon as I increase the voltage beyond 0.2 volts peak at the input, so here I've applied the small signal with a peak value of 0.201 volts. So corresponding to 0.201, the output volts peak, the output at the voltage at the output of stage 2 will be clipped off slightly at the top, because this is a very slight increase beyond 0.2 volts peak. That is why we observe very slight clipping in the output voltage of the stage 2, which produces a very slight clipping in the output voltage of stage 3. But as I go beyond by large amount, so this corresponds to 0.5 volts peak to peak. So this input voltage will produce voltage at the output of stage 1 of 1 volt peak to peak, which is the maximum allowed swing. So it is still a sine wave because it hasn't exceeded 1 volt peak to peak. So the stage 1 is being driven at its maximum swing. But that 1 volt peak to peak gets multiplied by the gain of the second stage, which is 10 units. So it tries to produce an output of 10 volts peak to peak at the output of stage 2. But the maximum swing at the output of stage 2 is 8 volts peak to peak. So that is why we observe clipping of the voltage at the output of stage 2 at 8 volts peak to peak or 4 volts peak. And then that clipped waveform is multiplied by 0.9, and the output is still, this magenta curve, which is the final output, is still chopped off at its peak. So please note that in these illustrations, I have ignored the effect of non-linearity of the transistor, which changes which makes the GM, which is the slope of the IC/VDE curve. So that GM becomes variable for large voltages. It becomes variable over the swing of the input voltage, and hence it causes the output voltage to swing by different amounts in the positive and negative directions. So we have already discussed this effect of distortion in the output of the amplifier. But in this case, I have ignored that effect. And as a result, you can see that the positive and negative swings are symmetric. So I've ignored this effect of non-linearity for the sake of clarity and simplicity. So we can, so given, apart from the analysis, given the maximum symmetric swing constraint of the multi-stage amplifier, we can design the multi-stage amplifier, the individual stages in the multi-stage amplifier for individual maximum symmetric swing. So in this example, I'm using the same three-stage amplifier circuit as shown here. But now I assume the gain of the first stage to be 10 volts, the gain of the second stage to be 100 volts, 10 units, the gain of the second stage to be 100 units, and the gain of the third stage is kept the same, 0.9 units. And I need to design the individual stages for maximum symmetric swing such that the overall maximum symmetric swing is 10 volts peak to peak. So one way of doing that is to designate the maximum symmetric swing of the output stage as the maximum symmetric swing of the overall multi-stage amplifier. That is 10 volts peak to peak. And then just keep on dividing that swing by the gain of the current stage, the stage under consideration to get the maximum symmetric swing of the previous stage. So the maximum symmetric swing of second stage is the maximum symmetric swing of the third stage divided by the gain of the third stage. So this gives me 11.11 volts peak to peak. And then the maximum symmetric swing of the first stage is the maximum symmetric swing of the second stage divided by the gain of the second stage. Maximum symmetric swing of the second stage is maximum symmetric swing of the third stage divided by the gain of the third stage. So I get this overall expression. So 11.11 divided by 100 is 10 over 0.9 divided by 100. So this gives me 0.11 volts peak to peak. So again, using the definition of the maximum symmetric swing, you can see that the maximum symmetric swing of the overall multi-stage amplifier obtained this way is equal to 10 volts peak to peak. Because the first quantity in that definition, which is the maximum symmetric swing of the third stage, it is 10 volts peak to peak. The second quantity is maximum symmetric swing of the second stage times the gain of the third stage. So this is again 10 volts peak to peak. And then the third quantity was maximum symmetric swing of the first stage times the gain of the second stage and the gain of the third stage. So this is again this value multiplied with this equal to 10 volts peak to peak. So for this particular example, all of these terms here in the definition, they are equal to 10 volts peak to peak, and hence the minimum is equal to 10 volts peak to peak. So this is one way of designing the individual stages for the maximum symmetric swing, given the constraint on the maximum symmetric swing of the overall multi-stage amplifier. So now we move on to different types of multi-stage amplifiers, and depending upon the interconnection of individual stages, there are actually two types of multi-stage amplifier configurations. The capacitive coupled multi-stage amplifiers, in which the output of an amplifier stage is connected to the input of its following stage through a capacitor. And as we will see, it enables separate DC analysis for all the individual stages. The other configuration is direct coupled configuration, in which, as the name suggests, the output of an amplifier stage is directly connected to the input of the following amplifier stage of its successor. So here I show this circuit diagram of a capacitive coupled two-stage amplifier. So this is the source signal, which is capacitively coupled to this dual supply common emitter amplifier, which is then capacitively coupled to another dual supply common emitter amplifier, which is then capacitively coupled to this load RL. So this capacitor, due to this capacitor, the two stages, since are connected through this capacitor, this amplifier is called capacitive coupled two-stage amplifier. So at DC, when all of these capacitors are open circuited, you can see that this first stage is disconnected from the second stage. So the two stages are separated out, and they can be independently analyzed for the DC currents and voltages. So at DC, like I said, I can separately analyze these two amplifier stages. So looking at this amplifier stage, I can, as before, because at DC this just becomes a voltage divider network, and I can simplify the base side of this voltage divider network through this. So this is the same circuit as this. I've just drawn these two voltage supplies categorically, explicitly, and then I can apply Thevenin's theorem as before to find the Thevenin's equivalent circuit of this base side circuit of the voltage divided by network. And so this is the reduced or the Thevenin equivalent circuit of the first stage of the multi-stage amplifier. We've already done this before when we studied the voltage divided by network. So same can be done with the second stage, and then the DC currents and voltages, they are given by the usual expressions that we have studied before. So this is the Thevenin voltage for the first stage, Thevenin resistance for the second stage, base current, collector current, emitter current, output collector emitter voltage, and the corresponding quantities for the second stage. So here I've assumed that the current gain beta is different for the two transistors. So beta 1 is the current gain for the first transistor, and beta 2 is the current gain for the transistor in the second stage, which gives us alpha 1 and alpha 2. So the DC analysis is pretty straightforward in case of capacitive coupled multi-stage amplifiers. Small signal AC analysis is carried out by replacing the transistors with their small signal models. And since again I'm assuming that I analyze this, or I'm analyzing this circuit in the mid-band frequency range, I have replaced the coupling capacitors with short circuits. So this coupling capacitor between two stages has also been short-circuited, and I have ignored the internal capacitances of the BJT. So this is the overall AC equivalent circuit of the two-stage capacitive coupled amplifier, which is obtained by short-circuiting the two DC sources to ground. So VI1 is the input voltage to the first stage. Here I have replaced R. So I have replaced this parallel combination and this parallel combination with R7 and R7 respectively here. So this is R7 this is R7 and these are the two small signal models. And then this is the load resistance. Because of short-circuiting VCC to ground, RC1 appears here and RC2 appears here. So RI is actually equal to RI1, which is the input resistance of the amplifier. R01 is the output resistance of the amplifier, because this is the output of the amplifier. This is the output of the first stage of the amplifier. So R01 is the output resistance of the first stage of the amplifier, which is connected to the input of the amplifier. So RI2 in the second stage. So RI2 is the input resistance of the second stage of the amplifier. And then just before the load, R0 is the output resistance of the second stage of the amplifier, which is the output resistance of the overall multi-stage amplifier. So as you can see, RI2 acts as the load to the first stage. And since we have already derived the expressions for the input resistance, output resistance, voltage gain, current gain of common emitter amplifier, we can directly use those expressions that we derive for the common emitter amplifier without bypass capacitor, because this is the common emitter amplifier configuration without bypass capacitor. So we can directly use those expressions to find the small signal parameters for this overall multi-stage amplifier circuit. So input resistance seen looking into the base of the first stage, looking into this port has already been found. It was given by this expression. The only difference is that now instead of RL, we have RI2. So RI2, so when finding the input resistance, we can replace the second stage with the input resistance of the second stage. So the resistance seen looking into this port, which is made up of this node and ground, towards the right is RI2. So whatever is towards the right, I can simply replace it with Ri2. So Ri2 acts as RL for the first stage. So I simply replace RL in the expression we have derived for RIB. I simply replace RL with Ri2 and we'll get RIB for this circuit, which is the resistance seen looking into the base of the first stage. And the input resistance, which is the resistance seen looking into this port between which is made up of base and ground, is again has already been found. So in that expression, we simply replace RL with Ri2. And then the input resistance of the second stage, which is the resistance seen looking into this side of the circuit. So if you isolate this circuit from the rest of the circuit, then this is nothing but the common emitter amplifier without bypass capacitor. So we have already analyzed this before. So Ri2 is given by the same expression. Obviously, we have included subscripts 2 with the parameters to correctly label the small signal parameters. So R2 is the small signal resistance in the base for the second stage amplifier, second stage of the amplifier, and R1 is the small signal resistance in the base of the first stage of the amplifier, and so on and so forth. So by appropriately labeling these small signal parameters, we can use the expressions we have obtained before for the common emitter amplifier without bypass capacitor to find these three resistances. Now, in order to find the output resistance R0 here, output resistance R0 is found by short circuiting the input of the amplifier, which is Vi1. So by short circuiting Vi1, I am left with a circuit which is given by the small signal model here, this circuit of the second stage, and then this circuit of the first stage. So as I did for the input resistance of the amplifier, which acts of the second stage of the amplifier, which acts as the load resistance to the first stage of the amplifier, by short circuiting Vi, whatever is left of this circuit, so this circuit can be replaced with R01, because when I want to find the resistance seen looking into this side, which is the output resistance, it is the resistance seen looking into the output of the first amplifier, which is RC1, connected between this node and ground, and then solving this circuit to find R0. So R0 is found before RL by finding the equivalent, by finding the output resistance of this circuit. So in this circuit, I have replaced the first stage with R01, simply with R01, because the resistance seen looking into this side of the network, the resistance seen looking into the output of this circuit by short circuiting Vi1 to 0 is given by R01. So I can simply replace this part of the circuit with R01 for the AC equivalent circuit I use to find R0. So this circuit which I used to find R0 has R01 here connected, which models the output resistance of the first stage. And if you look closely, then this is exactly the same circuit we used to find R out of the common emitter amplifier without bypass capacitor. The only difference is that instead of R sig, we have R01. So in order to find R0, I will use the expression derived for R out of the common emitter amplifier without bypass capacitor by simply replacing R sig with R01. So this is the expression for R out of the common emitter amplifier. So I simply replace R sig with R01, and I find R0, which is the output resistance of the second stage, and is also equal to the output resistance of the overall amplifier. Output resistance of the first stage is given by the same expression as before, because now I want to find the resistance seen looking into this side. So I disconnect this circuit, I short circuit Vi, and I'm left with a circuit which I have solved before. It is the same circuit I used to solve for the output resistance of common emitter amplifier without bypass capacitance. So I can exactly use that exact expression we derived before to find the output resistance of the first stage. So this is the expression we derived for the output resistance of the first stage. this is the expression we derive for the output resistance of common emitter amplifier without bypass capacitor. So we can directly use it to find the output resistance of the first stage. Now, R out of the two-stage amplifier is actually the R out of the second stage. So R out of this amplifier is actually R naught by short circuiting V sig. So when we short circuit V sig instead of VI1, we get R out instead of R naught. So again, you can see that when I short circuit this V sig to ground, then the resistance seen looking into this side is simply R out 1. So in order to find R out here at the output of the multi-stage amplifier, I use the expression for R out derived for the common emitter amplifier without bypass capacitor by simply replacing R sig with R out 1, because this circuit now can be replaced with R out 1 because I'm short circuiting V sig. So replacing this circuit with R out 1, I can directly use the expression we derived for R out of common emitter amplifier without bypass capacitor to find the R out of the overall multi-stage amplifier. So I have simply replaced in that expression R sig with R out 1, where R out 1 is given by the same expression as before. So R out 1, if I go back to the original circuit, R out 1 is the resistance seen looking into this side by short circuiting V sig to ground. So we've already found this resistance, and we can directly use that expression to find R out 1. So basically, if I replace R naught 1 with R out 1, I'll get R out. So this is what I've done here, and R out 1 is given by the same expression as before. Open circuit voltage gain of the second stage is equal to the open circuit voltage at the output of the second stage divided by VI2. So if I disconnect load, then I designate this voltage as VOC2, and VOC2 over VI2 is the open circuit voltage gain of this common emitter amplifier. We have already found this expression before. So we simply use that expression as it is to get the open circuit voltage gain of the amplifier. Obviously, we need to make adjustments because we need to replace R0 with R02, beta with beta 2, and so on, R pi with R pi 2, and so on and so forth. Similarly, the loaded voltage gain is just the load voltage divided by the input voltage to the second stage. So we plug the load resistor back in and find the load voltage and take its ratio with VI2. So like I said, we have already found this expression before for the common emitter amplifier without bypass capacitor. I simply use that expression by replacing RC with RC2, RE with RE2, R0 with R02, beta with beta 2, alpha with alpha 2, R pi with R pi 2, and I get the loaded voltage gain for the second stage. Loaded voltage gain of the first stage is given by the similar expression. So loaded voltage gain of the first stage is the voltage VI2 while this stage is connected as a load to the first stage. So VI2 is the input voltage of the second stage, and since the second stage acts as a load to the first stage, so VI2 is actually the load voltage of the first stage. So VI2 divided by VI1 is the loaded voltage gain of the first stage. And again, it is given by the same expression as before. The only difference is that instead of RL, we have RI2 because the input resistance of the second stage acts as the load resistor to the first stage. So simply replace RL with RI2 in that expression. So this gives us the loaded voltage gain of the first stage. And then the overall open circuit voltage gain is given by the open circuit voltage at the output divided by VI1. So VOC2 over VI1 is VOC2 over VI2 times VI2 over VI1. So it is the product of this gain and this gain. And the overall voltage gain of the multi-stage amplifier is given by connecting the load back in. So it is VL over VI, VL over V sig. So VL over V sig is equal to VL over VI2 times VI2 over VI1 times VI1 over V sig. So it is the product of AB2, AB1, and VI1 over V sig is again the usual factor which takes into account the effect of loading on the input side. Using these expressions, we can find the overall voltage gain and open circuit voltage gain and the overall voltage gain of the multi-stage amplifier. Similarly, we can use the expressions we obtained for the common emitter amplifier without bypass capacitor for the short circuit and overall current gain of the configuration. So the short circuit current gain of the second stage is the output short circuit current divided by the input current. So the input current has been labeled as I2, I subscript I2. So this is the input current. So I replace RL with short circuit, and the current flowing through the short circuit is designated as IOS. So IOS over II2 is actually the current gain of short circuit current gain of this common emitter amplifier without bypass capacitor. So we've already obtained this expression. So we directly use this expression here. So we directly use this expression here to get the short circuit current gain of the second stage. And then the overall loaded current gain of the second stage is given by plugging the load back in and finding the load current and then taking its ratio with the input current of the second stage. So again, we have previously derived this expression for the common emitter amplifier without bypass capacitor. So we directly use that expression to find the loaded current gain of the second stage. And then we can find the loaded current gain of the first stage. So the second stage acts as the load to the first stage, and the input current of the second stage is the load current of the first stage, because the input resistance of the second stage is the load resistance to the first stage. So if I go back to the circuit, then this input resistance of the second stage is the load to the first stage, and the current flowing through the input resistance is then the load current of the first stage. So, and also I have designated the input current to the first stage as I sig. So by simply replacing RL with RI2, so by simply replacing this circuit with a resistor here labeled RI2, we can see that the simplified circuit becomes the circuit of common emitter amplifier without bypass capacitor with load connected, where the load is given by RI2 and the load current is given by II2. So again, I can use the expression for the loaded current gain derived for the common emitter amplifier without bypass capacitor to find the loaded current gain, which is given by II2 over I sig for the first stage. So I hope you can see that this square bracket is being closed by this square bracket here. So in that expression, I simply replace RL with RI2 because the load to the first stage is actually the input resistance of the second stage. And then the short circuit and total current gain of the multi-stage amplifier, they are given by finding the ratio of the output short circuit current to the input current I sig, which is IOS over I2 times I2 over I sig. So it is the product of, so short circuit current gain is the product of this gain and this gain, whereas the overall current gain is the ratio of the load current to the input current. So it is the product of IL over I2 and I2 over I sig. So it is the product of these two gains, these two current gains. As before, when we analyzed different amplifier configurations, after deriving the exact results, I use some approximations, some assumptions to give the approximate and more commonly encountered expressions for the small signal parameters. And in all of those assumptions, I essentially ignored R0. I took small R0 to be much greater than the other resistances in the circuit. So here again, if we ignore R0, that is, if we ignore our small R01 and small R02, then we can obtain these this set of approximate and more commonly found expressions for the capacitive coupled two-stage amplifier. So I leave this as an exercise for you guys to derive these results from these expressions, all of these expressions. So maybe I can do one for you. So RIB is then, if I ignore small r naught 1, then it means that I am taking small r naught 1 to be much, much greater than other terms. So the numerator is r naught 1, denominator is small r naught 1, so I'll be left with this resistance. Similarly, this factor will be 1, and then I'll be left with this resistance. And this factor will be 1, and I'll be left with this resistance. So this is what I've written here. This factor, and this factor. And then on exactly the same lines, you can derive the rest of the results. So as I said earlier, the direct coupling of multi-stage amplifiers couples the output of an amplifier directly with the input of the following stage. So here I show the circuit of a direct coupled two-stage amplifier. So the first stage is it's a dual supply multi-stage amplifier, and the first stage is a common emitter amplifier again without bypass capacitor, and the second stage is another common emitter amplifier without bypass capacitor. But for the second stage, there is no R1, R2. The DC currents and voltages in the first stage, they are used to bias the second stage as well. So the DC analysis for this circuit is rather a bit more involved. Now, as you can see that there is direct coupling between the two stages, and the two stages cannot be analyzed separately under DC conditions. So at DC, when I open circuit the capacitors, the output and input coupling capacitors, the source and load are disconnected, and I'm left with this circuit here. So the base side of this circuit, again, using the Thevenin theorem, can be simplified with a resistor and a source, and this in turn gives us this circuit, this reduced Thevenin equivalent circuit for the two-stage amplifier circuit, direct coupled amplified circuit under DC conditions. So I have replaced the R1, R2 circuit here with this Thevenin equivalent circuit. So this is the circuit I need to analyze for DC currents and voltages. So the DC current in the first stage can be analyzed as before by writing a KVL here on the input side. So I get the usual expression as before, and then using the current gain of the transistor, which is for the first stage is given by beta 1, I can find the collector current and the emitter current, this collector current and this emitter current. So where beta 1 is the current gain of the transistor in the first amplifier stage. And V Thevenin and R Thevenin, they are given by, so V Thevenin is the fraction of voltage across R2, and R Thevenin is the parallel combination of R1 and R2, as before. So there is nothing new here. We've already seen these expressions. However, the current through the base terminal of the second stage, IB2, is obtained by finding the current through RC1, because the current through RC1 divides itself into the collector current and the base current of the collector current of the first stage and the base current of the second stage. So the current through RC1 is given by the voltage drop across RC1 divided by RC1. So the current through RC1, which is denoted by IRC1, is the sum of the collector current of the first stage and base current of the second stage, and it is given by this expression in terms of the voltages. Because the voltage drop across RC1 is VCC minus VC1, and then VC1 is the same as VB2, because collector of the first stage is connected to the base of the second stage. So the voltage drop across RC1 is VCC minus VB2 over RC1. And then VB2, which is the voltage of the base of the second resistor with respect to ground, can be written as the sum of VBE2, the voltage drop across RE2, and minus VEE. So writing IRC1 as this, I can take IC1 to the other side to write IB2 like this, and then I can replace VB2 with the sum of VBE2 plus the voltage drop across RE2, which is given by IE2 times RE2, and IE2 is IB2 times beta 2 plus 1 minus VEE. So because of this negative sign, the signatures of these terms, they are reversed. Then I can take this term, which has this factor of IB2, this unknown variable IB2, onto the other side, simplify and solve, and this is the expression we get for the base current of the second stage, where again I have represented the current gain of the second transistor with beta 2. So beta 2 is the beta of the transistor in the second stage. So having found out IB2, I can find the remaining DC voltages and currents. So IC2 is simply beta 2 times IB2, IE2 is beta 2 plus 1 times IB2, and we can find the voltage across the collector and emitter terminals of the transistors in the two stages. So the total voltage of this node, the voltage of this node with respect to this node, which is VCC plus VEE, is divided into drop, or this total voltage VCC plus VEE can be written as the sum of the voltage drop across RC1, the voltage VCE1, and the drop across RE1. Similarly, this total voltage of VCC plus VEE can be written as the sum of voltage drops across RC2 and RE2 plus VCE2. So I can use these relations to find VCE1 as VCC plus VEE, VCC plus VEE minus the drop across RC1 minus the drop across RE1. Similarly, VCE2 is VCC plus VEE minus the drop across RC2 minus the drop across RE2. So using these equations, we can find the DC currents and voltages in the direct coupled two-stage amplifier. Then in order to find the small signal quantities of the direct coupled multi-stage amplifier, we need to analyze the AC equivalent circuit, which is obtained by short circuiting the DC voltage sources to ground. And since we are operating in the mid-band frequency range, we have short circuited the coupling capacitors, and we have ignored the internal capacitance of the BJT. So here again, I replaced the two BJTs with the small signal hybrid pi model. And because of direct coupling, the collector of the first stage is directly connected to the base of the second stage. So if you look closely, then this is actually the same circuit we used to analyze the AC, the small signal quantities for the capacitive coupled two-stage amplifier. The only difference is that there we had R7 and R7 Here we don't have any R7 So R7 is can be considered infinity, and we have replaced R7 with R7. So we don't need to derive the small signal parameters from the scratch. We can use the expressions we derived for the small signal quantities of the capacitive coupled two-stage amplifier by simply replacing in those expressions R7 with infinity and R7 with R7, and we will obtain by replacing in those expressions R7 with infinity, R7 with R7, we can directly obtain the small signal parameters for the direct coupled multi-stage amplifier. So this brings us to the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.